Our third speaker is Dr. Chen from another branch of SINOPEC called FRIPP. FRIPP locates at Dalian. It's northeast of China, and they are also running the Artificial Intelligence Center of SINOPEC.
Thanks, Professor Chen. My name is Chen and I'm from SINOPEC, Dalian Research Institute for Petroleum and Petrochemicals. I'm going to give you a presentation about the AI algorithms and models on the planning and scheduling in oil refinery industries. Well, first, let me introduce my company briefly. My company was the first founded Petroleum Research Institute of China, founded in 1953, about 70 years ago. You can see the picture. It's a very old building located in Fushu, and below is the pictures of some of the pioneering petrochemical technologies developed by my country. And now we are relocated, moved to Dalian, and we built one of the most advanced research institutions of petroleum. And the major business of my company is hydrogenation technology. We hold about 50% of the market in China. Today I'm going to talk to you about the new business of my company, which is planning and scheduling in oil refineries. The oil industry is a vital bridge between the raw materials, which is crude oil, and the products. Well, the process is so complex. All the reactions and transportations are at high pressure and temperature, and the process is continuous. The process networks are very complex. We can use different crude oils to produce same products. So the product variety is and the process is very flexible. And therefore, we have to use algorithms and models to optimize the whole process for planning, because all the oils are shipping from outside countries, start from 3 months before. So we must predict the next 1 to 3 months for all the plannings and scheduling. And according to our research, the planning business will affect the whole margin of the plant to about 10 to 30%, which is the most significant factor for all the processes. How we do that? We first need the precise data from process for process and unit operations, and we also need data from the market, like the price, like the demand and supply. So I'm going to talk about the 3 aspects, which is the challenges in the process modeling and the optimization models. The first one is, I believe, it's the interface between the process modeling and optimization model, because the 2 models are fundamentally different. We have to use some data transmission to communicate to the different models. The second one, we are thinking about expand the model horizon to investigate how the plants will be in the next 10 to 50 years. And the third one, we will use the model to predicting some downstream planning optimization process. So this is the recent work of us. First one is the interface between the process modeling and the optimization models. So in process simulations, we can model the reaction process very in a high accuracy. But in the optimization model, we have to linearize every equations. So we have to make approximations to linearize all the process simulation data. Well, the basic idea is simple, but when we apply the idea to industrial scenarios, it becomes complex. Because in the industries, we have so many simulation platforms. We have commercial simulators, we have in-house softwares, we have industry data. So all these data in different format and different style, we cannot efficiently model all those data inside our optimization model. So here's what we suggest. We introduced a new layer of data-driven HSV model. We train it with machine learning models. So all these models will be trained to a data-driven model, and we can unify all the data formats, and which is better for the industry staff to use, because when the whole plant is at your computer for optimization, you have to focus on the global optimization, so you cannot present a accurate process simulation for each unit. And use our middle layer, you can neglect all the detailed stuff, and you can focus on the global optimization. And we can use our in-house softwares for the hydroprocessing kinetic modeling. And we can also model all the unit operations with commercial platforms. And we can train all the machine learning models with the data-driven model. And you can see the picture below. When we integrate all those models in the optimization model for the planning purpose, it will bring a lot of deviations when we optimize the capacity of the whole plant. So this method bring the industry simple method to utilize all the process simulation data with a simple way, because the time is valuable in the industry. We have to do the optimization every day. We don't have time for all this data from this process simulation. But if we simplify all the process, it will be easier for us to use. And second one, we expand the model horizon. We are interested in what will the refining industry will be in the next 10 to 50 years. So we introduce more dimensions into the model. Usually we focus on the mass streams of the optimization model, because the mass streams represents the oils. We sell oils, we buy oils. But if in the future, the carbon tax will bring more expense on the whole process, and the hydrogen will be produced in a cleaning energy. So we have to focus on the different streams. We call them element streams, sulfur streams, hydrogen and the carbon. We focus all the items flow in the whole process. And we also introduced energy streams like electricity and steam and biogas. So when we add all these aspects to the model, then we can build a hyperstructure of all the refining plants. And when we use such model, we can observe at each different level of carbon tax and hydrogen cost what best configurations of the plants will be. So here's the carbon footprints tracked in the model. When we do such optimization, we not only get what we need to buy crude oil, sell products, we can also know how much carbon footprints are bringing in the products. So when the carbon tax is considered in the real world, we can know exactly how much carbon footprint in the product. Better predict the future, we also introduced a pricing system based on the machine learning model and the empirical model. So we can know at different times how the carbon and the crude oil will at different prices. We built about 200 cases for the investigation on all the different processes. We can, although when the hydrogen cost, hydrogen price, or carbon limitations and carbon taxes are different, what unit operations we prefer and what unit operations we don't like. And in the long-term prediction, we found that when the hydrogen cost is low because we have more renewable energy and the hydrogen becomes greener. And we prefer to add more hydrogenation units to the refining process. And if the carbon tax raises and the hydrogen technology is not there yet, we have high hydrogen cost, and the refining process prefers the fluid catalytic cracking unit with a lower hydrogen cost but higher product oils yields. So the model, the purpose of the model is to foresee what the refining plants will be in the next decades. And we can use such a model to predict the future and to re-engineer all the whole processes. And the last, something about the downstream optimization. When the oils is produced in the refining plants, we have to transport it and to the gas station terminals. Well, the process is simple, but there's something we must know in the whole process. We must know what's the demand and what's the supply we can provide. And use those data, we can make all the logistic plan and optimize it. But how to predict the demand? We tested all the models of machine learning. We tested transformers. Although the transformer model provides us a lower loss, but it fails to predict the daily data. So we tested all the models. We found LSTM was the best one. It's fast. Its accuracy can satisfy our needs. So we modified the LSTM model and introduced several dimensions like weather, price, events, and other production features. And the model accuracy is improved. We can now predict the demand on the special events, and the model becomes more practical. Here's some example about our predicts of demands. We can accurately predict the demand of diesel and gasoline in the gas station terminals. And use this data, we can build a logistic optimization model for all the transportation plans. We use this to design a software, and we can use this software to predict all the demands and generate a transportation plan and vehicle arrangement schedules for all the for the Hubei province, the product sale company. Here's some interesting part. We found that the transformer is not capable of predicting the daily demands. Some other models are very good, like the informal model, but the computation cost is too high. We have about 600 gas stations to create, which means we must model at least 1,000 to 2,000 models, and the model must be iterated at a week basis. So the computation cost is something we must consider. And we test all the models. Still, LSTM is the fastest one and has the lowest error. So we still choose LSTM. And this is something of our recent works. And we are now working on something else to introduce more AI technology for oil refining industry. So I'll give you some perspectives about how the industry will be and what the industry needs from the academic community. First one is a planning and scheduling business. We need more powerful nonlinear solvers to optimize the whole process. Well, the industries are desperate to embed highly nonlinear solvers to integrate process simulation and connect the models to the planning optimization models. We know all the equations, but we simply cannot integrate the process simulation model to the optimization model because no solvers can solve it. And the second one is the matrix one. We form a matrix. We found that in our industry, the matrix is so sparse. Seldom there's rare linear libraries can solve those kind of matrix, which means we need better operation of matrix to solve the problem. And the third one is a scale. SINOPEC has over 30 plants. We build a model with 3 million non-zeros in the matrix. And we need to solve it within 30 minutes, which is very hard for the conventional solvers. So if the academic community could provide a powerful solver to deal with all these problems, the industry will go to the next level. The second one is large language models. Large language models is a good interface between people and complex softwares. But there's a problem of the LLMs because LLMs cannot give you accurate and specific results because of its nature. But we found that in the planning business, all the data, results, and the decisions are in the form of natural language, and we don't need an accurate decision, but we only need a direction of the decisions. So LLMs are the best choice for the industry. So we are now working on training some large language models to understand all the planning process and providing us some valuable decisions. And we also require the model to analyze large-scale data and optimization results, which will help us to rapidly optimize the whole plant, even multi-plants. The third one and the last one is the generative AI. Generative AI is a popular subject in recent years. Someone had used the generative AI to design catalysts and materials. But in the refining industry, I have never seen a model could design a catalyst for the refining industry. The problem, I think, is we lack data because the refining industry is So it's a black box in the industry. We do not know what happened in the reactor, so we cannot provide enough data for the generative AI model. But I believe this will change if we optimize the model, if we have gathered more data. So I believe in the future, the generative AI will be a powerful tool for the audit process. We expect generative AI to design catalysts. We expect them to automatically model the whole plant. We also expect the AI model to design reaction loops and re-engineer all the process. So if we can reach the goal, we can generate more data for the AI model to train itself. So I believe someday we could use generative AI to produce more opportunities for our industry. And that's all.